Properties of fluids. This chapter discusses the fundamental properties of fluids that form the foundation for all topics in fluid mechanics. A fluid is defined as a substance that can flow and continuously deform under any applied shear stress. Understanding fluid properties is necessary to explain phenomena such as pressure, flow, and energy transfer. All analyses in this course rely heavily on how these properties are modeled. By mastering these basic characteristics, engineering applications can be analyzed in a more systematic and consistent way. Lesson Plan Fluid Mechanics 1. The course structure is arranged progressively from basic concepts to internal flow applications. Each chapter builds the understanding required for the next topic. The chapter on fluid properties serves as a bridge between fundamental concepts and static and dynamic flow analysis. This sequence is designed so students understand not only formulas, but also their physical meaning. By following this structure, learning becomes more logical and integrated. Learning outcome. The learning outcomes emphasize mastery of basic fluid properties and the continuum approach. Students are expected to understand the meaning of viscosity and its effects on flow. In addition, surface tension effects and capillarity phenomena are also important focuses. The ability to calculate and interpret these phenomena are essential in engineering applications. These outcomes prepare students for more advanced fluid analysis. Illustration of a droplet and surface tension. This image shows how a liquid droplet forms due to the balance between pressure, gravity, and surface tension. The droplet shape is not accidental, but results from the minimization of surface energy. Surface tension plays a key role in determining the geometry of the fluid interface. This simple phenomenon appears in many engineering and natural applications. From this example, it is clear that fluid properties have real physical and visual effects. Intensive versus extensive properties. Extensive properties depend on the size of the system, while intensive properties do not depend on system size. If a system is divided into two parts, extensive properties are also divided, but intensive properties remain the same. Examples of extensive properties are mass and volume, while temperature and pressure are intensive. This classification is important for thermodynamic and fluid mechanics analysis. Understanding this difference helps in constructing correct balance equations. Continuum idealization in fluid flows. In most flows, the length scale of the system is much larger than the mean free path of molecules. Therefore, the fluid can be treated as a continuous medium. Properties such as density and temperature are assumed to vary smoothly and continuously. This approach greatly simplifies engineering analysis. Without this assumption, flow analysis would become extremely complex at the molecular level. Gas as a continuum. Even though there are empty spaces between gas molecules, the number of molecules in a small volume is still extremely large. This allows gas properties to be treated as continuous quantities. At the macroscopic scale, gas behavior remains predictable. The continuum approach is valid for most engineering applications. This is why fluid mechanics laws can still be applied to gases. Check your understanding. This slide is used to check understanding of the continuum concept in gases. The core of the question is how gas properties can be treated at the macroscopic scale. The correct answer reinforces the basic assumption used in fluid mechanics. This understanding is important before moving to other fluid property concepts. Short evaluations like this help strengthen core concepts. Density and specific volume. Density is defined as mass per unit volume, while specific volume is volume per unit mass. These two quantities are inversely related, so V equals 1 over rho. This concept is very important in almost all fluid mechanics and thermodynamics calculations. Many other fluid properties are expressed based on density. Therefore, density is one of the most fundamental properties of fluids. Specific gravity of substances. Specific gravity compares the density of a substance to the density of water at standard conditions. It is a dimensionless quantity and provides a quick way to judge how heavy or light a substance is relative to water. Substances like gold have very large values, while air has very small ones. This concept is often used in buoyancy analysis and material identification. With specific gravity, comparing material properties becomes much simpler. Supersonic bullet dynamics. This image illustrates the behavior of airflow when a bullet travels at supersonic speed. Air can still be treated as an ideal gas even at such high velocities. When the bullet pierces the air, expanding shock waves are formed. Behind the bullet, a turbulent wake appears due to the disturbed flow. This phenomenon shows how compressibility and high-speed effects influence fluid behavior. Check your understanding number 2. This slide is used to check understanding of phenomena occurring in high-speed flows. The main focus is recognizing the role of shock waves and turbulent wake. The question links the concepts of ideal gas behavior, shock waves, and turbulence into one physical phenomenon. The correct answer confirms that high speed produces very sharp pressure changes. This evaluation helps ensure that the basics of compressible flow are understood. Vapor pressure overview. Vapor pressure is defined as the pressure exerted by a substance's vapor when it is in phase equilibrium with its liquid. Under this condition, the number of molecules evaporating equals the number condensing. The value of vapor pressure strongly depends on temperature. The higher the temperature, the higher the vapor pressure. This concept is essential for understanding boiling and cavitation processes. Saturation pressure of water. The saturation pressure of water increases very rapidly with temperature. At 100 degrees Celsius, the saturation pressure equals atmospheric pressure, so water starts to boil. Above this temperature, a small increase in temperature can cause a very large increase in pressure. This data shows how sensitive saturation pressure is to temperature. This relationship is very important in thermal and fluid system analysis. Cavitation damage. Cavitation occurs when local pressure drops below the vapor pressure, causing vapor bubbles to form. When these bubbles collapse, extremely large local forces are generated. These forces are what cause severe damage to material surfaces. This example shows how destructive cavitation can be in fluid systems. Therefore, cavitation is a critical consideration in pump and turbine design. Illustration of power plant and electrical outlet. This image shows the connection between large-scale power generation and household energy use. Energy produced in a power plant must go through several conversion stages before being used. Fluids play a crucial role in transferring thermal and mechanical energy in power plants. This visual example emphasizes the role of fluid mechanics in modern energy systems. Without understanding fluid properties, such systems cannot be properly analyzed. Forms of energy in power transmission. Nuclear energy is converted into thermal energy, then into mechanical energy in the turbine. This mechanical energy becomes rotational kinetic energy. The magnetic field in the generator then converts it into electrical energy. This chain of conversion shows how different forms of energy are interconnected. Fluids act as the main medium for transferring and converting these energies. Check your understanding number 3. This slide checks understanding of the type of energy associated with turbine motion. The question links the concept of kinetic energy to the electricity generation process. The correct answer confirms the role of motion as an intermediate step in energy conversion. This evaluation ensures that the energy conversion chain is properly understood. This concept is very important in power system analysis. Energy in fluids. Internal energy represents the microscopic energy of a stationary fluid. For flowing fluids, the concept of enthalpy is used, which includes internal energy and flow work. This distinction is important in the analysis of closed systems and flow systems. In many engineering applications, using enthalpy is much more practical. This concept is fundamental in the analysis of turbines, pumps, and heat exchangers. Fluid compression. Fluids experience a reduction in volume when subjected to higher pressure. Although liquids are often considered incompressible, this effect becomes significant at high pressures. This phenomenon is very important in applications such as hydraulic systems. Understanding compressibility is required for more accurate analysis. Therefore, pressure and volume change are always related in fluid behavior. Illustration of surge tower and household arrestor. This image shows two scales of pressure surge protection systems, a surge tower for large systems and a small arrestor for household use. Both work on the same principle, which is to absorb sudden pressure increases. Pressure surges can occur when flow is stopped abruptly. Without protection, pipes and equipment can be damaged by high mechanical stresses. This visual emphasizes that fluid mechanics phenomena occur from large to small scales. Water hammer arrestors. Water hammer is a pressure surge phenomenon caused by very rapid changes in flow velocity. Surge towers and small arrestors are designed to absorb these pressure spikes. With these devices, the temporary pressure energy can be safely dissipated. This protects pipes, valves, and equipment from damage. This concept shows the importance of considering transient effects in fluid system design. Check your understanding, number 4. This slide checks understanding of the main function of surge towers and arrestors. The focus is on system protection, not on improving flow performance. The correct answer confirms that the main purpose is to absorb pressure surges. This evaluation emphasizes safety and system reliability. This understanding is important for safe pipeline network design. Natural convection. Natural convection occurs because of density differences caused by temperature differences. Warmer fluid becomes lighter and moves upward, while cooler fluid moves downward. This phenomenon can be observed in warm air rising above a hand. Natural convection is very important in ventilation and passive cooling. Many engineering systems use this mechanism without fans or pumps. Volume expansion. Volume expansion describes how the volume of a substance changes when temperature changes at constant pressure. Substances with a large expansion coefficient experience significant volume changes. In contrast, substances with a small coefficient change only slightly. This concept is important in designing systems that experience temperature variations. Without considering expansion, design errors can occur. Sonic speed effects. When an aircraft's speed approaches the speed of sound, air begins to compress and accumulate. This can form vapor clouds due to changes in pressure and temperature. The transition to the sonic regime produces shock waves. This phenomenon shows the relationship between flow velocity and the thermodynamic properties of air. These effects are very important in high-speed aerodynamics. Volume expansion coefficient of water increases as temperature rises. The graph shows that this change is quite significant between 20 degrees Celsius and 50 degrees Celsius. This means the sensitivity of volume to temperature also increases. In precision systems, even small changes must be considered. This data is important for calculations involving liquids over a wide temperature range. Check your understanding number 5. This slide is used to reinforce the relationship between temperature and the volume expansion coefficient. The question checks whether the increasing trend is understood. The correct answer strengthens the interpretation of the previous graph. This short evaluation helps ensure that the quantitative concept is not only memorized but understood. This is important before moving on to pressure wave analysis. Pressure wave propagation. A pressure wave can propagate in a fluid due to a small disturbance, such as piston motion. At the wavefront, pressure, velocity, and density increase. This phenomenon is the basis for understanding sound propagation. This concept is also important in the analysis of water hammer and transient flows. By understanding pressure waves, dynamic fluid behavior can be predicted more accurately. Control volume in wave motion. The analysis of pressure waves is performed using a control volume that moves with the wave. In this frame, changes in fluid properties at the wavefront can be analyzed systematically. Pressure, density, and enthalpy increase after the wave passes. The wave speed relative to the fluid becomes an important parameter. This approach forms the basis for deriving the equation for the speed of sound in fluids. Sound speed and lightning. The speed of sound in air depends on temperature, so in warmer air, sound travels faster. The average speed of sound in air is about 340 meters per second. The time delay between lightning and thunder can be used to estimate the distance to the lightning strike. If the delay is very small, it means the lightning is very close. This concept shows that pressure wave propagation has practical applications in everyday life. Sound speed factors. The speed of sound increases significantly as temperature rises. In addition, the type of fluid also affects the speed of sound. Under the same conditions, sound travels much faster in helium than in air. This shows that the thermodynamic properties of the fluid play an important role. This understanding is important in acoustic and aerodynamic applications. Check your understanding number 6. This slide tests the main factors that influence the speed of sound in a fluid. The question focuses on the role of temperature and molecular properties of the fluid. The correct answer confirms that molecular weight and temperature are the dominant factors. This evaluation ensures that the relationship between fluid properties and wave propagation is understood. This concept is the basis for understanding the Mach number. Mach number variations. The Mach number is defined as the ratio between flow velocity and the speed of sound. For the same flow velocity, the Mach number becomes larger at lower temperatures because the speed of sound is lower. This is important in the analysis of supersonic flight. Changes in ambient temperature can significantly alter flow characteristics. Therefore, the Mach number must always be interpreted together with the thermal condition of the fluid. Drag force on bodies. Drag force arises due to viscosity and friction between the fluid and the surface of a body. The characteristics of drag differ between airflow and water flow. The shape of the body strongly influences the magnitude of the drag force. Therefore, streamlined designs are used to reduce drag. This concept is very important in the design of vehicles and structures moving in fluids. Laminar flow between two plates. The fluid velocity changes linearly from one plate to the other. The lower plate is stationary, while the upper plate moves with constant velocity. This velocity gradient generates shear stress. The flow is orderly and can be predicted mathematically. This model forms the basis for understanding the concept of viscosity. Newtonian fluid behavior. In a Newtonian fluid, shear stress is directly proportional to the rate of deformation. This relationship produces a straight line on the shear stress versus deformation rate graph. The slope of this line represents the viscosity of the fluid. Fluids with higher viscosity have steeper slopes. Many engineering fluids, such as water and air, can be treated as Newtonian fluids. Check your understanding number 7. This slide checks understanding of the relationship between shear stress and the rate of deformation. The core of the question is to recognize the characteristic behavior of Newtonian fluids. The correct answer confirms that shear stress is proportional to the rate of deformation. This evaluation reinforces the basic definition of viscosity. This understanding is essential before discussing non-Newtonian fluids. Shear stress in fluids. Newtonian fluids show a linear relationship between shear stress and deformation rate. Non-Newtonian fluids exhibit more complex behavior, such as pseudoplastic and dilatant behavior. Bingham plastics require a yield stress before they start to flow. This classification is important in many industrial applications. By understanding the fluid type, the correct flow model can be selected. Viscosity and pressure. Dynamic viscosity is relatively insensitive to pressure. In contrast, kinematic viscosity can change significantly because it depends on density. When pressure increases, fluid density also increases. This causes changes in kinematic viscosity. This concept is important in the analysis of high-pressure flows. Viscosity and temperature. For liquids, viscosity decreases as temperature increases because intermolecular forces weaken. In contrast, for gases, viscosity increases with rising temperature due to increased molecular activity. This opposite behavior is important to understand in flow analysis. Temperature becomes a key parameter in determining fluid flow characteristics. Without considering this effect, calculation results can be significantly inaccurate. Dynamic viscosity of fluids. Viscosity values vary widely among different fluids. Glycerin has very high viscosity, while gases like hydrogen have very low values. Temperature changes can drastically alter viscosity, especially for viscous liquids. Therefore, viscosity data must always be associated with temperature conditions. This information is important in selecting working fluids and designing systems. Dynamic viscosity trends. The general trend shows that liquid viscosity decreases with increasing temperature, while gas viscosity increases slightly. This difference comes from different molecular mechanisms in liquids and gases. Experimental graphs and data show a clear contrast between the two types of fluids. Understanding this trend helps in predicting flow behavior. This is very relevant in thermal and industrial process applications. Check your understanding number 8. This slide tests understanding of how viscosity changes with temperature in liquids and gases. The question compares the two opposite behaviors. The correct answer confirms that liquid viscosity decreases, while gas viscosity increases. This evaluation strengthens conceptual understanding, rather than simple memorization. This concept is important before moving on to surface tension. Surface tension effects. Surface tension causes water droplets to form nearly spherical shapes on leaf surfaces. This phenomenon also allows small insects to stand on water without sinking. This force acts at the fluid interface and tries to minimize surface area. This visual example shows that surface tension has real mechanical effects. Many small-scale phenomena are dominated by this force. Molecular forces in liquids. Molecules inside a liquid experience balanced attractive forces from all directions. In contrast, surface molecules are pulled inward because there are no molecules above them. This imbalance of forces is what creates surface tension. As a result, the liquid surface tends to contract. This molecular explanation helps in understanding the physical origin of surface tension. Liquid film stretching. In a liquid film, surface tension acts along the surface and pulls the wire inward. To increase the surface area, an external force must do work. The magnitude of the required force is proportional to the wire length and the surface tension value. This experiment shows how surface tension can be measured. The concept of work and surface energy becomes very clear through this illustration. The surface tension of water decreases as temperature increases. Mercury has a very high surface tension compared to most common fluids. In contrast, gasoline and soap solutions have much lower values. These differences explain why droplet behavior varies greatly among fluids. This data is important in many process and materials engineering applications. Forces in bubbles and droplets. Surface tension acts along the curved surface. A bubble has two surfaces, so the surface tension effect is doubled. As a result, the pressure inside the bubble is higher than the outside pressure. This force balance is what maintains the nearly spherical shape. This concept is important in understanding emulsions, foams, and two-phase processes. Check your understanding number 9. This slide tests understanding of the cause of the pressure difference between the inside and outside of a bubble. The focus is on the role of surface tension force. The correct answer confirms that this force is what makes the internal pressure higher. This evaluation strengthens the link between force and pressure at fluid interfaces. This understanding forms the basis for the topic of capillarity. Contact angle and wetting. The contact angle indicates how well a fluid wets a solid surface. Wetting fluids, such as water on glass, have a small contact angle and tend to spread. Non-wetting fluids, such as mercury, have a large contact angle and form droplets. The value of the contact angle depends on the interaction between the fluid and the solid surface. This concept is very important in coating processes, cleaning, and microfluidics. Meniscus in capillary tube. A meniscus is formed due to the combination of surface tension and adhesion forces between the fluid and the tube wall. For water in a glass tube, the contact angle is small, so the meniscus is concave. This meniscus shape affects the height of the liquid column in a narrow tube. This phenomenon is very important in precise volume measurements. Understanding the meniscus is also important in capillarity analysis. Capillary action in tubes. For water, adhesion forces dominate, causing the liquid to rise in a narrow tube. For mercury, cohesion forces dominate, causing the liquid level to fall. The direction and magnitude of the height change are determined by fluid properties and tube diameter. This phenomenon is known as capillary action. This concept is widely used in wicking systems, absorbent paper, and biological tissues. Forces in capillary action. Capillary rise occurs because of the upward force due to surface tension along the tube perimeter. This force must balance the weight of the liquid column inside the tube. At equilibrium, the upward force equals the downward weight force. From this balance, the capillary rise height can be derived mathematically. This concept shows the direct relationship between surface forces and gravity. Check your understanding number 1. This slide tests understanding of the main cause of capillary rise. The focus is on the balance between surface tension force and the weight of the liquid column. The correct answer confirms that the upward surface tension force supports the liquid column. This evaluation reinforces the concept of force balance in static fluid systems. This understanding is important in many engineering and scientific applications. References. This slide lists the main sources of figures and materials used in the lecture. The primary reference comes from the book by Chengal and Chimbala, which is a standard reference in fluid mechanics. Using this source ensures that the material presented follows international standards. References are also important for independent, deeper study. With clear references, the academic quality of the lecture can be justified.